Welcome back, everyone, to our last to our last podcast for those who are watching now on the podcast, and our last real lecture and workshop session of the year. As we've sort of said before, or I'll say on the next slide, we're still meeting next week, but that'll just be kind of an open workshop session to work on projects. So this is the last new content at all, and so we'll get to it. So as the comic says, just to sum up, just before we get on with today's stuff, to sum up a bit, this comic is about all these books that you might see in the bookstores and stuff that say things like, oh, teach yourself, in this case, C++, but they could easily say teach yourself Java or Python or Matlab or something in 21 days. And as this suggests, I agree with them that there's no real way to learn this stuff in 21 days. Unless you do go back and create a time machine and go back and kill your younger self, 10 years earlier, after learning this stuff. But I think for only having, one school year, and as we've had 18 meetings, I think we've covered. Well, you guys would probably agree we've covered a lot. Some might say too much, but I think you guys have picked up a lot, and that. Even if you never use this again, I think these skills will be useful. But if you do continue to develop these skills, I think you probably know enough now that you can kind of continue teaching yourself and reading up on the internet. And hopefully, what we've tried to do here is give you enough background, but to kind of find more things out for yourself. And a lot of the problem sets and things I've been trying to encourage figuring things out for yourself and looking things up online, and kind of doing a mixture of testing things out and trying for yourself versus looking at how people already do it. So anyway, today's the last lecture type content, but hopefully people will want to maybe continue in some way or another with programming in the future. Okay, so as we've got here, what we're going to end up doing here is do a little bit of stats and talk a little bit about plotting and data presentation. We're going to keep it simple again because, I think it's we're probably all a little worn out at the end of the semester and could stand to take it kind of easy. So, it'll be a pretty easy session today, I think. I encourage you guys to kind of follow along with me in the Matlab stuff today because it's pretty easy stuff that we're going to be typing in and playing around with. Not necessarily conceptually easy, but short scripts. And we're not talking about Psych Toolbox at all today. So we are done with Psych Toolbox. Now we're just talking about kind of pure Matlab today and what you can use it for besides presenting psychology, cognitive psychology experiments. So we were going to talk about this with regard to EEG and fMRI and do some more advanced stuff. We're not going to really talk about that today. I'll show you some stuff that you can do with EEG or fMRI, but really, until you get your hands on some real data, it's all kind of theoretical anyway. And originally I had sort of planned to talk about how you could do MATLAB type stuff with Python. And again, that would be kind of interesting if we had more time, but I think it's not totally necessary. So what you'll find is Python advocates will of course say oh, there's no need to use MATLAB. Ever, basically, because Python's free and Python can do anything Matlab can, but freer and better. I had this argument with John Pierce, the creator of PsychoPy, earlier this year in the UK. And it is true there are Python modules you can import that basically emulate all the functions in MATLAB, but of course MATLAB does it all natively. So if you have a copy of MATLAB, now it is expensive, so you either have to have it at a university or have a lot of money or, go through some legally questionable steps to get it. But, if you do have access to MATLAB, there are a lot of things that are just very easy to do in MATLAB that are not too hard to do in Python either, but sort of require bending Python a bit to make it do what MATLAB does naturally. But anyway, we won't be talking about that, but if people are interested, we could, talk about that offline. Okay, just in terms of dates and things, so everyone got their problem set in last Friday, good for you. Problem set 10 is out a little bit later than all of my internal deadlines, but hopefully if you guys had to stay out of the lab all weekend anyway, hopefully that didn't affect people too much. And you've still got basically 10 working days to wrap it up. I think it will not be too difficult. Hopefully people will enjoy this one, kind of. So that's due a week from Friday. I am working on marking previous problem sets, but I've got lots of other things to look over, so I'm getting to it as fast as I can. But, you know, in theory, you shouldn't need anything from previous problem sets to do this one. You know, it might help you to have the keys and things a little bit here and there, but, you know, if you have the kind of problem that requires the key, you know, come to me and I can share some code with you or show you what I did before the key is actually available. Okay, so projects are due on the 2nd of May. I think that's is that a Thursday? Something like that. And again, we can talk about more next week about submitting those, but like we said, you can just kind of zip up all of your files that you need to run the project and include just you know, some brief, like a readme.txt kind of release notes of what I need to do to run the project. You know, if I need to configure any files or anything like that, or if I need to know about bugs or how to control the task or whatever it is. You know, anything like that that you need to say how to do, you'll need to include some minor amount of documentation just telling you how to run the thing. But, you know, don't have to do a write-up or anything like that. You've already done that in the proposal. Okay, and like we said, this is the last regular lecture. So next week is all workshops. So, you know, if you're a podcast-only viewer, adios after this. Anything else before we jump into the last little lecture thing? Okay. So I've just got a couple slides for you on data analysis and data presentation. So Matlab, of course, is really good for data analysis of all kinds. And of course, that's mainly what it's actually for, right? The Psych Toolbox is, you know, we don't use Psych Toolbox in Matlab because Matlab is necessarily so great for things like Psych Toolbox. And in fact, a lot of the core functions of Psych Toolbox are not actually written in MATLAB language. I think they're written in C. And MATLAB has ways that you can write functions in the C language and then kind of still run them from within MATLAB. So, you know, Psych Toolbox is mainly used with MATLAB because there are some things that are very nice about MATLAB for psychology and neuroscience. And a lot of us are using it anyway for our data analysis, so it makes sense to kind of keep everything in the same family. And it's, you know, a pretty good it's not the best general purpose programming language probably, but it's a pretty good general purpose programming language. So it does make some sense to present cognitive tasks and things with MATLAB, you know, via Psych Toolbox. But mainly what MATLAB is, of course, is about manipulating numbers and matrices and so forth, right? And I've tried to emphasize this again and again, that everything's a matrix. Really, everything you're doing is matrix calculations whenever you're presenting images or you know, sounds or anything like that, right? It's all just numbers, really, at heart. So MATLAB's great because it's got a lot of any sort of common mathematical or statistical thing you might want to do is implemented in MATLAB. MATLAB, like the basic MATLAB, only includes some functions, but there are these toolboxes you can add on, and I think we have access. I'm not sure exactly which toolboxes we have installed here. I asked for these statistics and image processing toolboxes, and I think we did get those. So, you know, you can get sort of extra stuff, but even in the basic MATLAB, you have most of your common mathematical and statistical functions. And of course, they're designed to run on large matrices very quickly, so you don't have to do them one at a time. So, you know, if you need to run one t-test, well, you don't for one t-test, you don't even need SPSS or anything like that. You can just run those in Excel. And you certainly don't need anything as specialized as MATLAB. But if for some reason you want to run 100,000 t-tests across a very large data set and then do something more sophisticated with that, MATLAB's really the way to go there, right? Because you can't do 100,000 t-tests by going through SPSS and clicking, you know, selecting 100,000 variables, right? You want a language that you can program to read in a large data file or generates a large, you know, amount of data somehow, and then analyze it. And because MATLAB does things in a matrix manner, it can do something like a t-test on a whole bunch of values simultaneously. You don't have to do all of them individually. So that's really the advantage of Matlab is you can do these operations in like massive parallel, and for something like fMRI or EEG or something like that, where it is true that you have an EEG, you have data from maybe 128 electrodes on the brain, and you're pretty much processing them all the same way. So you want to do these operations, many times all at the same time, and Matlab's pretty good for that. So it's really good for things like EEG and fMRI, and of course all kinds of other data sets in other fields as well. It's not just for psychology and neuroscience. Okay, so even for small data sets, there are ways that Matlab can be useful. So one of them, of course, is what we would call Monte Carlo simulations. I don't know if people are familiar with this term, but it's a pretty common term in computer science and statistics. And the idea here is basically, sometimes you get into a situation when you're doing statistics where there isn't really a statistical test that does what you want it to do, right? I mean, we would like to think that, and maybe we've even taught you that in stats class, t-tests and ANOVAs and correlations and regressions and so forth are all you'll ever need. But sometimes you want to test a hypothesis that can't easily be tested using any classical statistics, or it's not really clear how you would do it. And in those cases, one nice thing about having computers nowadays is that you can run what are called Monte Carlo simulations. And the idea here is it's like spinning a roulette wheel, right? Because the whole idea of statistics is we want to know whether the data we see are unlikely to have been observed by chance, right? So the nice thing about a computer is we can create a lot of random data sets that simulate what the data would look like if it were chance data, right? If it were just random data. And we can see how often a result that looks like ours comes up from purely random data. And if it comes up infrequently, we can generate a p-value based on these Monte Carlo simulations, based on spinning the roulette wheel many times, right? So like, you call it Monte Carlo simulations, right? Because the idea is like, well, let's see if we, if you wanted to test whether like the roulette wheel is what's the word? Is like not legitimate. If it's weighted, or if it's cheating somehow, right? So it wins too often on the number 7 red, for example. One way you could do that is you could spin it, 100 times and then do some, or a few hundred times and do some sort of t-test or something like that. But the other thing you could do is just compare it, for 1,000,000 spins against a known set of random values and see if, see if you get something different, basically, in the truly random versus the, versus what you observe, right? So that's the idea of these Monte Carlo simulations. So you typically you do things like randomly shuffle your data or generate random data and then test thousands and thousands and thousands of times. Depends on what you're doing, but 10,000 iterations is a pretty common value. And you see basically, if your p-value or your alpha is 0.05, you see if you obtain a result that looks like yours less than 5% of the time. And if you do, you say what you've got is significant. And in theory, of course, these Monte Carlo simulations should agree with classical statistics. So you can also verify how classical statistics work that way. And we'll do a little bit of that today. Okay, it's also pretty good for data plotting. I personally, we teach, well, you guys learned how to, make figures in SPSS. Now we teach in the first year how to do it with Excel as well. And I used Excel for most of my graduate career, but more recently I've become frustrated with our friend Excel for many reasons. One of the main reasons being that the Mac version is just awful these days, but it crashes all the time, and it's very frustrating. So I've started making all of my figures actually in Matlab. So we've seen a very small amount of this. Like I've already shown you guys the plot function. I'll show you some other functions today that you can use to plot your data. They're often really great to just do like a quick basic plot, just to have a quick idea of what your data look like. You don't need anything fancy a lot of the time. But then, of course, if you want to tweak the settings, you can actually make very professional-looking graphs as well. So I'll show you a little bit of that. We don't have time to get into it much, but I'll show you a little bit of what's possible. The only problem is you do have to spend a fair bit of time getting it just right, because the settings that you can tweak to make these graphs and things there's like millions and millions and millions of them. Well, not millions, but there are many of them. and they can be tweaked in lots of little ways. So I finally wrote a really fancy script to draw nice bar graphs, for example, because I use a lot of bar graphs. And it probably did take like a day or two of my time just writing that script. Now then it saved me a lot of time punching data into Excel, because then I can just give MATLAB a new data set and have a nice looking bar graph in 5 seconds. But it does take some time to figure out how to make nice graphs in MATLAB. Okay, so pretty much the rest of today is all demos. Anybody got any questions or anything before we kind of jump in? Okay, so let's just play around a little bit. And like I said, most of these are pretty short little pieces of code that you can try out with me. It may not be, I don't know how interesting this will be to people. I find MATLAB useful all the time for testing out things about statistics. Because sometimes you're trying to do something statistically and you're like, well, does this really work? Is this result valid? It doesn't happen too much when you're just doing t-tests and ANOVAs, but when you get into more advanced stuff, you're constantly like, well, is this really the right way to analyze it? So a lot of times it makes sense to kind of make a little test of your own using random data or so forth, using these Monte Carlo techniques, and see how things work out for yourself. So I'll show you just a couple examples of this. So let me make a new directory. Oops. Not lecture 180. Lecture 18 code. Lecture 18. Okay, so let's do the first demo. Now this is gonna, hopefully this doesn't break your brain remembering this. But this is a pretty simple statistical concept that I think works really well to demonstrate in real life, and it only takes about 20 lines of code to do. So let's make a function called central limit demo. You can call it whatever you want to, but that's what I'm calling mine. So you guys may or may not remember, probably, let's just assume you don't remember what the central limit theorem is from your statistics classes. But the idea of the central limit theorem is this idea in statistics that how if you're doing a t-test or an ANOVA or any sort of parametric statistic, you generally want to have normally distributed data, right? And when you get into studying like why statistics are the way they are, you get into these ideas like sampling distributions. And again, you guys probably haven't talked about sampling distributions in a long time. You probably forget what they are even. But the central limit theorem is the idea that even if the data in the population are not normally distributed, if you take samples from that population and take the average enough times, those averages of the various samples will actually be normally distributed regardless of the shape of your original distribution. Okay? It'll make a little bit more sense once we do the demo, I think. And you'll get to see kind of how it goes. So let's just kind of jump in and we'll sort of explain as we go. I'm calling this central limit demo. I'm going to define a few variables first. So whenever I do something that I'm iterating a bunch of times, my variable name that I usually use is called nits, which is number of iterations. So this is how many times we're going to run it. Let's just start doing this like 20 times, and we'll crank it up. And what we're basically going to do is we're going to generate a bunch of random samples of data. So let's say our sample size, let's say it's about 100, which is a lot for a cognitive experiment, but not that much for a survey or something like that. So let's say we have 100 observations in every sample. And what we're going to actually end up doing is some histograms. So in the histogram, we have to decide how many sort of bins to put the data into. So I'm going to say it looks nice when we have 20 bins. And that'll be all we have to define up front, I think. So when this function runs, the first thing we're probably going to want to do is make some figure windows. So MATLAB's got a command nicely called just figure, like that. And it'll pop up a figure window. Now that's not very helpful by itself because it doesn't have anything in it. And actually, if you call something like plot, so if you want to say like, let's plot the numbers 1 to 10 for some reason as a line graph. Not surprisingly, it looks like a straight line going up from 1 to 10. you'll see that if you use something like plot, it will automatically pop up a figure window for you. But sometimes it's nice to use this figure command if you want to put up multiple figures and tell Matlab which one to draw into. So you'll see an example of why this is useful. So I'm going to call this variable fig1 and just say fig1 equals figure. And what that does is fig1 is going to be, again, one of these things called like a pointer or a handle or something like that. It's like what you get when you make a window in Psych Toolbox. So it's just a number, really. But the number, when you give it to a Matlab function that knows how to handle figures, tells Matlab basically like where to look up in its internal knowledge about what figure windows are open. It tells Matlab which figure that you're referring to. So it doesn't really create an object, it just gives you a number to refer to this figure by. So we can actually do this with the debugger and you can see. But basically, this is just going to let us, a little bit later, tell Matlab what figure we want to draw into. So we're going to do that twice. Oops, figure 1 and figure 2. And then what we're going to do, I don't think I've really used this function in Matlab very much, but there's a function called pause. All it does is pause and wait for a keyboard press. So when I'm doing a quick little demo like this, what I often like to do is just pop up the figure windows first and then pause so that I can kind of arrange them how I like. Because then once the demonstration starts going, the figures are going to go nuts and you can't always drag them around then. So this will let me kind of arrange all my little windows before anything starts. Okay. So now I'm going to do the demo. And so let's do it this way. So I'm going to make a little for loop that says for I equals 1 to nits. I'm going to go ahead and close off that for loop. That's good practice, by the way, to just go ahead and close your for loops as soon as you make them so that your MATLAB syntax checker thinks it's all right. Otherwise, like until you close your for loop, MATLAB's like, this code cannot run. So it's always nice to kind of like get your warnings cleared out as early as possible. And it, you know, you can't forget to close it off at the end then. So we're going to make a for loop that goes, you know, for the number of iterations we specify. So right now we're just going to do it 20 times. And I'm going to make some data, and it's going to be random data. So I'm just going to make random numbers in the size, sample size by 1. So I'm just going to make, in this case we said our sample size is 100. So I'm going to get 100 random numbers in a column, right? And remember the rand function by default gives us numbers between 0 and 1, right? So we're going to have 100 random values, 100 random decimal values somewhere between 0 and 1. And then let's get the mean of that. So conveniently, we don't have to add them all up and take the average. MATLAB has a function called mean. So we're going to get the mean of it, but we're going to want to store the means for all of our random data sets. So we're going to put that in a vector, or a matrix also. Okay. Now this is a little, well, there's a couple warnings we get here. We stayed away from a lot of these MATLAB warnings because if I taught you guys how to fix every warning MATLAB ever gives you, this class would last about 7 years. But I'm going to teach you about one of the common ones today. And I've already been like kind of secretly fixing this sometimes. So if you mouse over this, it gives you 2 warnings. One of them, the top one, is hopefully pretty obvious to you why we get it right. The value assigned to the variable means might be unused. MATLAB's pretty nice about this because, you know, basically it tells you, hey, you've made this variable, but you never use it for anything. So maybe you didn't mean to do that. Now, it's a little annoying when you're in the middle of programming because obviously as you write each line of code, you're often generating a value that you haven't written, you know, the next line of code yet that uses it. But it's actually very useful to get those messages when you're done coding because it'll remind you, you know, basically, maybe you've created a variable and forgotten to use it. Maybe you have a typo somewhere. So sometimes if it warns you, like, hey, sometimes it'll give you the warning, hey, you've made this variable and you never use it. Other times it'll tell you, hey, you're using a variable and you don't appear to have actually assigned it a value yet. Both of those are helpful because oftentimes it's just like a little typo, or sometimes you name it fig in one place, but then you want to call it figure somewhere else or something like that. So sometimes you just forget the names you use, so it's good for reminding you of that. But the other error here that we get is the variable means appears to change size on every loop iteration. Consider pre-allocating for speed. And what that's basically saying is Matlab runs fastest if it doesn't have to change the size of things. The idea here is that, like, we haven't told Matlab, we told Matlab how many times we're running this for loop, but what we're doing here is basically saying, like, the first time through the loop we say the first item of means, set that equal to the mean of our data set. The second time through the loop, set the second item to the mean of the data set, right? Or in other words, that's what we do if you remember when we did that end plus 1 thing. If we said, do the equivalent thing of saying, like, means end plus 1, right? Because that makes the next item beyond the end of the current list equal to something, right? But Matlab doesn't really like it that much when you do that, because basically it has to go to a lot more work and spend a lot more CPU time. Essentially what it has to do is it has to destroy the old variable and create a new one with a different size every time you do that. So what Matlab's telling you is your code will actually run much faster if you allocate all the memory you're going to need ahead of time and then just fill in the slots as you go, okay? So we can clean up that error message if we want by just creating this variable ahead of time. So I could say something like means equals zeros nits by 1. So what that's going to do is say that means is going to be a vector that's number of iterations, a column vector that's number of iterations by 1, right? So it's just a column of numbers. So because we're going to make one value every time we go through this for loop. So nits by 1 would be the right measurement. So this will clear up our error or our warning message here, right? Because now we're just replacing zeros with something, but we're not actually having to allocate a new variable with a different number of slots. Does that make sense to everybody? It's like saying, it's like each variable is a little like bookshelf or something with a bunch of holes in it, right? So of course it's much faster when you're putting a new item into the bookshelf to have a bookshelf that's the right size, and just take out one item or put one item in, versus to have to like build another bookshelf that's one item bigger every time you want to add a new item, right? So it's good to have all your space allocated ahead of time and then just slot things in. The only catch with that is we have to keep in mind that we have to put something in there at first, right? Because you can't have, in Matlab, you can't have an empty space in the matrix. It has to have something in every space. So what we're putting in, and that makes sense, right? Because basically what these spaces are computer memory. Computer memory has to have a value, right? You can't just like turn off that little bit of the RAM chip. It has to always be on with some value. So we can't just fill it with zeros. We just have to make sure that we replace all of these zeros with a value later on. Now one way I can be sure of this is if I want to, instead of making them zeros, and this is what I did in the actual demo, there's a special Matlab variable called nan, which means not a number. So like if you try to divide 0 by 0, you get nan, because that's not a number. It's a special number that indicates when something is not a number. And the nice thing is if we had we can actually have a matrix that has like a bunch of numbers in it. Let's say like A equals 1, 3, 5, nan. You don't really have to type it in capital letters, but you can. So it can be treated just like any other number. But the nice thing is that in Matlab, if you try to do most calculations with a nan in the list, like if we try to get the mean of the A matrix, you get out nan, right? Because the average of 1, 3, 5 in nan is also not a number, right? If you try to add 5 plus not a number, you get not a number, right? Because anything that you add to something that's not a number is not a number, right? So one nice thing we could do is instead of making the list full of zeros, we can make it full of nans. Whoops, nan. Well, the only difference that's going to make is if somehow I screw up my code, it's going to be obvious to me when I get to the end, because any operation I try to do with those means is going to give me a nan because I didn't replace a nan with an actual value. It's a little bit more sophisticated than you'll ever. Both of those things that we just did are a little bit more sophisticated than you really need to do in this class. But again, if you ever get into sort of big data analysis, this pre-allocating all of your memory thing, it's really important. I mean, it speeds your code up by a large percentages. So it is important to do that kind of thing. The NAND thing, that's really, it's sort of like defensive driving. It's like defensive programming. Like the idea of like trying to use coding practices that like anticipate the errors you are likely to make and defend against them. So, you know, again, it's a little bit, you know, you guys are still learning how to program in the first place, but the more sophisticated you get, the more you learn what the errors are that you will tend to make, and the more you learn to like build in little techniques to prevent yourself from making those errors, or at least to catch yourself when you do. Okay, so far all we've done in the loop is create some random data, taken its mean, and we've slotted that into a list of means. And then let's now draw some stuff into these figure windows. So what I want to draw in each figure window is a histogram of the random data I just generated. So what I'm first going to do is say fig 1. Oops. Now that does something a little bit different than when I just called figure up here. So when I called it up here with no arguments, and I guess, sorry guys, Matlab doesn't force you to put these little parentheses or brackets in when you're calling a function with no arguments, but I realize it's clearer for you guys if I get into the habit of doing this, because then you can see that they're functions. Otherwise, it's a little ambiguous what they are. So Matlab doesn't require that like Python does, but it's probably good practice for me to do it. Okay, so up here where we call figure with no arguments, that means create a new figure. If we call figure with an argument, what that really means is set the current figure for drawing to whatever figure I give it, right? So here, we created a new figure and called it fig 1. Here we're telling it, all right, let's draw into fig 1 now, as opposed to whatever the other current figure was, okay? So by default, the current figure is whatever the last figure is that was created. So if I foreground figure 1, that means I'm not drawing into figure 2, as I would have been otherwise. Okay, so now we're going to use a very simple command called Hist, which makes a histogram. Hopefully you guys remember histograms. We'll get to see it in action soon enough, so if you don't, no fear. And all you give it is your data that you want to make a histogram of, and you can optionally tell it how many bins to make. So in other words, how many bars to draw. So we'll tell it 20 bins, because we define bins up here to be 20. And then let's also draw something into figure 2. And let's make a histogram also here. And what I'm going to want to make a histogram of here is a histogram of all of the means of the population that we've generated so far. So in other words, the first histogram is going to be our current random data set. The second histogram is going to be the means of all the random data sets we've made so far. So that'll be our means from 1 to I, right? Because if we're on the ith run of our for loop, we've only generated means so far from 1 to whatever number I is right now. And everything below that is going to be nans, right? So we only want to go through the period that's not, or through the range that's not nan. And again, we'll draw that with bins number of bars. And then let's throw another pause in here so that we pause and wait for a key press at the end of each loop, okay? So let's just run that first and see how that goes. So here's our two figures. We've created our two figures, and then it pauses for us to do whatever we want to. So this is a good opportunity to kind of go like this so we can see our two figures side by side. And then when you're ready, you can press any key. All right, so this pops up our first iteration, right, which is to say, here's a histogram of 100 random pieces of data, right, with 20 bins. Hopefully you remember what a histogram is, right? So a histogram tells you for each range of numbers on the x-axis, so from like 0 to 0.05, 0.05 to 0.10, 0.10 to 0.15, 0.15 to 0.20, and so on, how many values in the data set have that fall in that range, right? So this tells me that there are six of our random numbers were between 0 and 0.05, looks like a lot, like 11 were from 0.95 to 0.1, right? Now in theory, if this is truly random, uniformly distributed data, which it pretty much will be because Matlab's random number generator is good, in theory we'd expect, since the values range from 0 to 1, and then we're drawing 20 bins, right? We told it to draw 20 bars. In theory, we should expect exactly 5 values on average in each bin, right? Because the random number generator is supposed to give us random numbers between 0 and 1 with like flat, even probability, right? So if it's equally likely that we'll get each number between 0 and 1, then it should just look like 5s across the board. Although, of course, because it's random, or because we're taking a random sample, there's going to be noise in that, right? So obviously it doesn't just come out to all 5s, but on average it should be all 5s, right? Now, the histogram for the first iteration is not that useful. The average is probably somewhere around 0.5. But it's not going to be meaningful until we have more values. So let's go ahead and hit any key. I'm just going to hit return to run a second iteration. Okay, so now we've got a different random data set on the left, a new histogram. Now this histogram at least makes a little sense because it says, all right, one of our means was around 0.47, another of our means was around 0.52 something. Let's run another iteration. All right, here's another random data set. Again, it looks like they're, on average, they are pretty evenly distributed. There are some peaks and stuff, but they don't appear to be in the same place every time. Another mean somewhere around 0.51. And if we keep going, all right, so this is, the histogram on the right is not that interesting yet, right? Because so far it's just a bunch of values. It doesn't look like too much. So what we really want to do, if we want to prove the central limit theorem to ourselves, I'm just going to close all my figures. I could have clicked the close buttons, but I find that Matlab on the Mac crashes more often for some reason when I click the close buttons on the Windows. So what we're going to do is run this for a lot more iterations, okay? So let's do a couple of things here. First of all, let's make the number of iterations, let's increase that to like 100, first of all. And instead of pausing for a key press every time, we're going to just pause for a certain amount of time so it doesn't go by too fast. So we're just going to pause. This is kind of like wait sex. This is the Matlab built-in version of wait sex in Psych Toolbox. In Psych Toolbox we use wait sex because wait sex is very precise. But in Matlab we can just use pause, and that's fine. We just don't have to get Psych Toolbox involved for regular Matlab code. So pause is fine. This says pause for 1/100th of a second. Which is really just enough time to make sure that it finishes updating the figure windows before it draws the next one. So pause with no arguments, again, waits for an actual key press. It pauses indefinitely. Pause with one argument tells Matlab how long to wait before moving on with the code. So now what this is going to do, if we just make those two changes, it's going to do more iterations and not wait for our key press every time it goes. So let's try that. Hopefully this will look a little bit more meaningful to you as we go on. So again, what we're seeing on the right here is a histogram of the means of all the random data sets that we're generating over on the right? So the idea of the central limit theorem is that even though, on average, these are supposed to be flat distributions, and a normal distribution would have a hump, right? These are supposed to be flat distributions. But over time, we're supposed to, the means of those distributions, even though these are not normally distributed, this is going to end up being normally distributed. Now, does it look normally distributed? All right, some not so sure. But it has, does it look flat, I guess is one question. It does not look flat, right? So, like a normal distribution, it has a bit of a peak in the middle. Seems to be kind of falling off towards the sides. Now the question is it truly going to be a normal distribution? And of course, this is the problem with these Monte Carlo simulations is you need to run a lot of iterations before you really start to see what things look like. It's the law of large numbers, right? You need a lot of numbers to really see what things look like in the long term, and get over sort of minor sampling variations. So let's increase the number of iterations a lot to 10,000. Now, we don't want to actually draw all 100,000 of these, because you see it's actually pretty slow to draw these figures, right? So, because obviously it's taking more than 1/100th of a second. Like, even though we only tell it to pause for 1/100th of a second, these drawing operations, whoa, what was that? Oh, shoot, I forgot that thing. If I use the laser pointer, it starts Matlab going. All right, can't use the laser pointer. Okay, oops, there's that bug. If I try to click on that window that didn't actually close, it always crashes Matlab. Okay, so what's happening is it's really slow to draw these histograms, right? So what would speed things up if we're doing 100,000 of these? It's pretty quick to do the actual calculations. So let's add one more variable in here. Let's call it draw every. Let's just draw one out of every, oops, draw every. Let's just draw every 100th iteration, okay? So that's just going to say, you know, generate 10,000 of these and only stop every 100 times and actually give a visual update, right? Otherwise, just kind of keep generating the numbers and updating them, but don't actually draw anything. And of course, the way that we're going to have to do that is let's only do these drawing things. So if we want to do something only every 100 times, you have to think about how you would do that, right? So basically we want to do it when I is 100, when I is 200, when I is 300, and so forth, right? So what would we use to determine when that's true? Well, what is true of the numbers 100, 200, 300? They're all multiples of 100, right? Which means if you divide them by 100, there's no remainder, right? So we can use our old friend mod. So if the mod of I with our draw every value is 0, so what that's saying is I is whichever iteration we're on, right? If we're drawing every 100, if I is like 100, then if you take the remainder of I divided by 100 and it's 0, that means we're on number 100, number 200, and so forth. And if so, we do all that drawing stuff. Otherwise, we do nothing, right? So we don't have to have anything else in our if statement. We can just say end. So now this will only draw an update every 100 times through, which means we should get 100 updates, right? Because there's 10,000 as 100 times 100. So let's try the central limit demo again. Again, if you don't remember central limit theorem, this is maybe not that cool, but it is a good way to demonstrate it to yourself if you're having trouble doing statistics stuff, but you know how to program. So every time through here, we're generating 100 samples, and you can see the shape of this it's taking some pretty nice shape. It's still a little lumpy, but it's clearly got a different shape than these flat distributions over here, right? It's probably just about done, I think. Maybe not. I did do that right? There's 100, 100s. Okay, there we go. All right, so forget about this. This is just some random piece of data, so forget about that guy. Take a look at your distribution here of all the means of those random data sets. Does that look like a normal distribution now if we run it 100,000 times? Kind of does, right? And it should, because that is the central limit theorem. The central limit theorem says, regardless of what our original distribution looks like, whether or not it's normal, the distribution of the means of a bunch of samples from that population will look normal. And that's important for statistical theoretical reasons that are not important to us right now. This is just a demo of how this general principle works. Now, I guess it's not worth like getting into the mathematics or the ideas of the central limit theorem too much, but this is a good example of like if you didn't like if you were smart about programming or if you knew about programming, but you were just starting to learn statistics and you wanted to prove this to yourself, this is how you would do it, right? This is how you'd say, okay, if I do enough if I take enough samples from a population, I can see that the means are normally distributed, even though the original samples, or the original population that I drew the samples from, was not normally distributed, right? Okay, hopefully that make some sense, kind of. Do people get that working? Or do you need to take a break and debug that, or? Okay, so that's one thing you can do. Now that's not that exciting, really, I know. But it could get more exciting, I think. So let's do this. Okay, so let's build on this a little bit, because there is a point to this eventually, I promise. Let's do a couple more of these little demos that are quick to do, and I'll explain them as we go. This won't take quite as much time. So I'm going to save this code. I'm going to call it, instead of central limit demo, I'm going to call it something like normal, non-normal demo. Tells me that I should probably rename my file, or my function. So I do that. Okay, so most of this, actually, we can kind of keep about the same. The point of this demo would be to say, all right, well, I've just shown that the central limit theorem works with non-normally distributed data. So if I wanted to compare normally distributed data, so sometimes, you may want to get some normally distributed data from Matlab, right? Because in real life, your data should be probably normally distributed, right? If you're doing reaction times or measuring heights or IQs or something like that, you should get a normal distribution in your data set. Fortunately, Matlab does have a built-in function to give you normally distributed data if you want it. And I'll prove that to you right now. So let's just call it A again. That's fine. So that one is called rand n for normal. So if you want normally distributed random data instead of uniformly distributed random data, right? So regular rand just gives you a random value between 0 and 1, kind of plucked randomly with even probability. Rand n gives you a number from a random number, but from a normal distribution. So there are going to be more values around 0 and fewer values the higher and lower you go. So just to prove that to you, let's get 1,000 by 1 random values. Remember your semicolon, or they will all print out. And if I want to just do a quick histogram of that, let's do a quick histogram of that with 20 bins, or 20 bars. See, that's a pretty nicely normally distributed graph, right? So that's saying that, in this set of random numbers I just got, now it gives you, rand n gives you data from a standard normal distribution, which means it has a mean of 0 and a standard deviation of 1. So what that tells us is, that if you remember how your standard deviations work, that 68% of our data should be between -1 and 1. About 95% of our data should be between -2 and 2. 99 point something percent of our data should be between -3 and 3, right? So it gives us random but normally distributed data, right? And if we wanted to prove those things to ourselves about randomly distributed data, we could say something like, here's an interesting thing you can do. This may be helpful in your problem sets and so forth, hint, hint, and your exams to know this little trick. So one thing we could do, if you remember, one thing we said that you can do in Matlab is if you do a comparison. So let's say if we want to know how many of these numbers in this random normally distributed data set have values greater or less, let's say between greater than -1 and less than 1. Okay, so between -1 and 1. So one way we could do that is we could ask how many of these numbers have absolute values less than 1, right? Now in theory what that should tell us is, looking at that histogram, the number of values between -1 and 1 should be about 68% of the population, right? Because that's how standard deviations work. So let's say, now if we want to get the absolute value of A, that'll give us, if we do abs of A, so here's A by itself, is all these numbers, right? absolute value of A, or abs of A, doesn't actually, it's not nothing about abs, like abdominal muscles, but it gives us the absolute value of all these, right? And if we want to test whether all of the, or which of these numbers have an absolute value less than 1, we can say, well, which of abs of A is less than 1? So that gives us 1, or a logical true value, wherever the absolute value of the number is less than 1, or 0, where the absolute value is greater than 1. Now here's where the trick comes in. Although logical values can only be 1 or 0, you can sum them up, and Matlab is smart enough to give you the sum of all the 1s and 0s. So if I want to know how many numbers in this data set of these 1,000 numbers have an absolute value less than 1, I can just say sum of all those true or false values. Look at that. How perfectly distributed is that? That's better than we would ever have expected. So 680 out of 1,000 random numbers generated from a normal distribution have values between -1 and 1, right? So that's exactly what you'd predict from statistics. And if we want to see how many fall within 2 standard deviations, we could change the 1 to a 2. That's not bad, 96.2%. And actually, it's I think it's 1.96 standard deviations is actually the 95% threshold. So that's pretty close, right? And I don't remember how many are. I think it's like 99.2% are supposed to fall within 3 standard deviations of the mean. Yeah, so that's pretty close again, right? Or maybe it's 99.7. I don't remember. Okay, so this proves to us that we really do have randomly or normally distributed random data, right? Anyway, the point is, so step 1 here is let's try this previous demo, but test both normally distributed random data and the previous random data that's not normally distributed and see if it looks any different, right? So let's keep all this stuff the same. Let's make 2 new figures. Okay, and then what we're going to have to do is make 2 sets of data now. So let's just call this, data uniform. And I'm just going to go ahead and rename all of those to data uniform, meaning it was drawn from a uniform distribution, right? The histogram is flat. So that's what we were generating before. Now let's call this a new one, data normal equals rand n sample size by 1. So we're just doing another random data set that's normally distributed. And actually, so now we're going to need 2 values for the means of those things, right? So let's call this means uniform. Just go ahead and rename all those to means uniform. And let's call this one means normal. And we'll set that to do the same thing, man nits by 1. All right, so we've made these data sets. We can calculate the means of the normally distributed random data. Right, so that's just taking the mean. And now, every time we want to draw, let's do the histograms for the uniform data, but then let's also copy and paste that, make this figure 3 and figure 4, and change data uniform to data normal, and means uniform to means normal. Okay. So what this is going to do is just let us prove to ourselves that the central limit theorem works for both normally distributed and non-normally distributed data, because what should happen is we'll see that the distributions of the individual samples look a lot different, but in the long run, the distributions of their means should look pretty much the same. Again, this is sort of kind of building to something. It's nothing that exciting, but we'll see how that goes in just a minute. All right, so now this is going to make 4 figure windows. So I'm going to try to, they're going to overlap a bit unless I can resize them kind of. So you can resize these the usual way. And you can actually write scripts to resize your Matlab figure windows too, I believe, but it's kind of a pain. Okay, so now we've got our 4 windows. Hopefully I typed everything right after spending all that time arranging my windows. Okay, so now what we've got here are uniform distributions on the top left, right? Normally distributed random data on the bottom left. And then on the top right and the bottom right, we have the histograms of the, basically what we call the sampling distribution, right? Or in other words, the histograms of all the mean values from each of these sets on the left. And what you should see, now they're going to be shifted a little bit because Matlab auto-scales the ranges. So like, it looks like we had one sort of, oh, the other thing is that they're going to have different means actually because the mean of the random data is going to be 0.5. The mean of the normally distributed data is going to be 0. But basically, kind of look the same. Now MATLAB is auto-scaling them differently because apparently there was one like freakishly large value by random chance in the top data, right? So MATLAB automatically scales these axes to whatever range the data are in. So it's sort of auto-scaling the one on top to be a bit skinnier than the one on the bottom. But you can see that they're both normally distributed. They both have the peaks at about 1,000 items, right? So in the end, they're probably going to look pretty similar, actually. By the way, because drawing the figures is kind of slow, you can actually see like every time we call figure, it highlights, you know, the window that we've indicated as our current figure. So you can kind of see like how it's highlighting and then drawing into each window in sequence, right? Okay, so we're probably almost done here with our simulation. Again, not the most interesting, but it's basically showing us that central limit theorem tells us that there should be no difference in this distribution and this distribution, even though the underlying distributions they were drawn from were very different. And that's pretty much the case. Again, these are sort of auto-scale differently, but I can manually reshape the graph a little bit if I want to, just to scale the numbers right. And yeah, they look about the same, as they should. Okay, so the real question is why do we care about this? And one of the reasons we might care is because we make certain assumptions when we do things like t-tests, right? So you might be worried, for example, if your data are coming from a one thing you might wonder is, if your data are coming from a non-normal distribution, can you still do things like t-tests or whatever on them? So what I'm going to do is, I'm going to save this again as normal, non-normal, demo 2. And what we're going to do now is say, like, all right, well, we've shown that the sampling distributions are not that different. But what if we were to actually do t-tests on all these data sets? Are we going to get a different number of true and false positives from normally distributed data as opposed to non-normally distributed data? Now, again, this is random data, so we should get exactly 5% false positives, right? Because we say we take p-values less than 0.05, so 5% of the time we should get p-values like that, right? So basically what we might want to do is say, all right, well, let's see how bad it gets if I don't have normally distributed data. If I have uniformly distributed data, how is that going to affect my t-tests, and can I trust my p-values that I get out of them, right? So instead of means now, let's not track means of these populations. Let's track p-values. So let's make p-values for uniform and normal data. And we're still going to go through, one thing I'm going to do actually is to put everything in the same range. I'm going to subtract 0.5 from the uniformly distributed data. So what this is going to do is, now it's going to make it random data. Instead of the 0 to 1 range, it's going to put it in the minus 0.5 to 0.5 range, right? So now both the uniform and the normal data should have a mean of 0, right? All it does is kind of shift all the values left by half a unit, right? And now instead of, what we're going to do is we're going to add one line of code here, because you'll see one nice thing that the Matlab has built in. If we do help t-test, it's got t-tests built in, right? So if we want to, if we want to t-test a bunch of values, let's say we've got like, well, let's just take, let's say A is equal to 20 random values. Actually, let's 20 randomly distributed, or normally distributed random values. So here's 20 random values for A. So if we want to t-test, if we want to do a one sample t-test against a mean of 0, we can just say t-test A0, which is t-tests the mean of A against a test value of 0. And what the 0 tells us is that our hypothesis is not confirmed. So by itself, t-test just tells you whether or not you confirm the hypothesis. Now, oftentimes you might want to get an actual p-value out of the test. So to do that, you have to have two output values assigned to this, which is, oops. So let's call them like h and p for whether a hypothesis was confirmed and what the p-value is. So this will tell us not only whether or not our hypothesis was confirmed, but also what the p-value is. And you'll see that our hypothesis was not confirmed because p is 0.386, right? So if we do this again with different random data, hypothesis not confirmed, p of 0.18, different random data, still not confirmed. Nope. Nope. This is just what we do in real life. Run an experiment. Nope. Run an experiment. Nope, can't publish that. Can't publish that. Come on. This is what my real life feels like sometimes. Only it takes much longer to run the experiments. Ooh, almost getting there. All right, apparently. Ooh, getting a trend. We must be doing something right. All right, I'm never going to confirm this hypothesis. Okay, yay, look at that. I got a p of 0.01. I can publish this, right? All right, so, and you see when you do finally get some random data that, gives you a p of 0.01, then your hypothesis comes out 1, right? Because you've confirmed your hypothesis. Okay. So that's how you run a t-test in Matlab. Now, that's just a simple one sample t-test. But there's paired t-tests and so forth built into Matlab as well. So the point is here, if we want to see whether or not our false positive rate changes, depending on whether our data are really normally distributed or not, we can say, all right, let's do a t-test, get our h and p values. So let's test our data uniform against 0, and then say our p's from our uniform data will equal that p-value that we got out of that test, right? And then let's t-test. We can just reuse the same variables because we're only keeping them in the p's uniform and p's normal matrices, right? So we can reuse h and p, but test normal data against 0 and set our normal p's, this item, sorry, the ith item of p's normal to be equal to the p from that test. Don't worry about this error or this warning message. It's not worth getting into what those mean. Okay, so I think that's it. So since we changed our variable names, everything else should be okay. So what this is going to tell us is, if we run that one, first I have to arrange our 4 windows here. I'm going to do this kind of quick-like. So what this is going to give us is, on the left, it's just going to show us again an example of our random data that we've generated. And on the right, it's going to show us, now it's going to show us a histogram of our actual p-values, right? So it's going to basically tell us, like, in theory, what we should expect is a uniform distribution of p-values, right? Because when you do a statistical test, what should happen is, if it's random data, you should only get p less than 0.05, 5% of the time. You should get p less than 0.10, 10% of the time, right? So let's try this and see if it's true. So basically, you see on the left side, we're once again getting basically flat random data on the left, right? Whereas we're getting normally distributed random data, sorry, on the upper left, and then normally distributed random data on the lower left. On the right, we have the histogram of all the p-values we've gotten from testing those against a mean of 0. And hopefully we should have, an exactly flat distribution, a flat distribution of p-values in both cases, which it looks like we kind of are. Let's see if it keeps going, if it looks pretty even in the end. not looking too bad. So in theory, of course, the one on the bottom should look totally flat if we do enough iterations. The one on the top, I'd have to sort of do some reading, but it's shaping up to look pretty flat as well, right? So it doesn't look like it's skewed in any particular direction, which is good news, right? Because this means that if you collect real data and the distribution of that data is not so normal, if it's flatter than expected, right? It doesn't seem to be causing a huge problem for the overall. It doesn't look like we're getting p less than 0.05 any more often or any less often than if the data really are normally distributed, right? Now that's not to say you should ignore, when you do your tests in SPSS, you should ignore like the normality tests that you do. But if your data are not normal in this particular way, it doesn't seem to cause a huge problem, right? Okay, so that's all done there. I know this is not so exciting to you guys probably, but like, you know, if you like to play around with statistics, that's pretty awesome, I think. Maybe not. So anyway, the main point there though is that you can make some kind of cool, well, not so cool, but you can make histograms, you know, and take a look at your data, and you know, it's a good way to kind of peek at your data and figure out what's going on in it and so forth. So it's probably time for a break. Any questions so far? Anybody having any difficulties or anything? Okay, so we'll stop for the moment. Okay, so here we go again. Now again, I realize this is not necessarily super exciting to do this stuff always, but I wanted to show you some examples of things that, you know, that you can do with analysis. And you know, of course, we don't have a lot of real data to analyze here, and if we did, we'd have to get into issues like loading in files and saving files and so forth that, you know, we just haven't got time for. So you know, I figured we could do some stuff with simulated data. The stuff you have to do in the problem set, I mean, you know, I also figured we could do some stuff that's slightly more complex and like, you know, interesting in a sense of statistics and stuff than, you know, just getting the mean of a bunch of numbers or something. Or, you know, I think in your problem set you have to get the mean response time and the standard deviation of the response time, which is pretty easy to do with the built-in function. So I figured we could do slightly more advanced stuff here today. And again, it's, you know, it's more interesting when you're doing it on your real data, obviously, because then you have a real reason to do it. So, you know, so as an example of a real life instance where I had to use this, for example, we did a study where we were classifying brain data. So the idea is, you know, we had fMRI data, and we were trying to use it to say, we had people like visualizing one of 4 different images, and we were basically using that to do essentially, you know, mind reading, brain reading, where we're using this computational technique to see if we could tell from looking at the brain data which of the 4 images people were visualizing. And you know, and we got results that were above chance, but of course one thing you want to check is that there's no like bug in your code that causes you to like get above chance findings, even though, you know, you don't actually have that in your data, right? So, you know, one thing we did is we generated random data, the same size and shape as the brain data, and found out that that was a chance, so that was good. You know, you can also do things like shuffle your brain images, you know, with regard to the condition labels. So if your condition labels don't actually match up to your real data, of course, you should also get, you know, chance performance out of that. So there are various things you can do in that regard. And if we have time, we might do a little bit of that with some behavioral data. But anyway, so we just talked about doing like, you know, most of those demos were about doing histograms and doing things like t-tests and stuff like that, just as an example. Of course, you know, if you do want to just do a bunch of t-tests on real data, now you know how to do that. And one thing to note is, again, you can do a bunch of them at once, right? So let's say, I'm just going to generate some random data, but let's say you had some real data. You know, so let's say you had 10 whatever, like you ran a survey and you had 10 questions, right? So you had 20 participants. Oh, actually, let's do this normally distributed just to make it have a mean of 0. Okay, so you had 10 participants. Here's data from, sorry, you had 10 questions and 20 participants. Here's data from those 10 questions and 20 participants. And you wanted to say, I want to t-test all of these at once to see if they have values different from 0, you don't have to go through and run 10 separate t-tests in Matlab. You can just say t-test this whole thing against 0. Now what it does is it assumes that your data that you want to t-test are in columns. So like each column is what you want to t-test against 0. But boom, it just gives you, oh look, we ran 10 tests and none of them were significant. It's almost as if the data were just random data we picked out of nowhere and did not have any real information in them. If you do it again, there's 10 more tests, still all zeros. 10 more, still nothing significant. We're not doing chance very well today. All right, so there we got one significant result. Of course, again, that's all in random data, so that's hence the need to do Bonferroni corrections or something like that, right? But you can do, if you need to do 10, 100, whatever t-tests at once, you can. Very easily, right? So you could just put your whole Excel file into Matlab and t-test them all at once. And of course, you would have to correct for multiple comparisons. So in real life, you maybe wouldn't do it exactly this way, but there are situations where this comes in handy. Okay, so on that note of what things you shouldn't actually do statistically, this is a demo I actually did for let's call this sample peaking demo. So I did this a year or two ago actually for a lab meeting. This is another like real life example of when I just sort of did this to see how it goes, but it actually came up with some pretty interesting results. So the question I was asking is, you all know that of course you have if you collect a sample size of say 30 participants and you then do a test, of course even if all of your participants don't actually show a significant effect, you've got a 5% chance that they will show an effect that's significant just due to chance, and that's the risk we take. But one thing people often do, which is not really the right thing to do, is they'll collect like 10 participants worth of data and then do the test, and if it's not significant, they collect a couple more participants, do the test, collect a couple more participants, and so forth, right? Now sometimes this makes, it's not right, but it does logically make sense that if you do have an effect, sometimes you just don't have enough people to see it yet, right? Because there's this whole issue of statistical power and sample size. And sometimes it's true that you totally have a significant effect, but it only happens when you have like 20 or 30 people. And so if you get just 10 and all you've got is a statistical trend, you might need to get 10 more people and then try it again, right? But the problem is, of course, if you don't decide on your sample size ahead of time and you just say, well, I'm just going to keep running until I get a significant effect, you're more likely to get a false positive that way than if you decide to collect a sample and just stop and don't peek at the data midway. So the question, I think, is how much of a problem is this if you peek at your data along the way? So, so let's find out, basically, and see how this goes. So, let's see something here. Okay, so let's say, for example, that I'm willing to collect as few as 5 participants and as many as 30 participants. And I'm a bad scientist, and I say, well, I'm going to take the first 5 participants' data and then test them to see if there's a significant effect. And if it is, I stop, and if not, I collect another participant and peek again. And if it's significant, I stop, and otherwise I keep going. And I'm not willing to collect more than 30 participants, but if I get a significant effect anywhere between 5 and 30 participants, I will stop. And the question is, what's our false positive rate going to be if there's really no real effect in the data, and it's just it's just random chance that we get an effect. So let's run this for about 2,000 iterations. Doesn't have to be anything fancy. And basically what I'm going to do then is I'm going to have a p-value for not only each iteration, but also each n between 5 and 30, right? So what I'm going to do is I'm going to say, all right, I'm going to collect 5 subjects, then add a 6th, then add a 7th. So for every number between 5 and 30, I'm going to have a p-value, right? Yeah. And basically, like, that means since I said I'm going to start with 5 subjects, they're going to be all zeros in the first 4 columns of this. But that's easier than kind of dealing with other consequences. Okay. So let's say, have a matrix of whether or not our hypothesis was confirmed. So that'll also be zeros that are nits by max n. Okay, so we've just kind of done this thing again where we pre-allocate our data so that we don't get MATLAB complaining about speed. And actually, this is kind of slow, so we will want lots of speed. There are probably... Yeah, there are totally ways I could speed this up. This is actually not very good code now that I look at it again, but that's okay. It'll be all right for our purposes because it's a little bit easier to understand this way. So just to show ourselves that it's working, one thing I'm going to do is say if mod of I100 equals 0, so every 100 iterations, we're going to display current iteration and then change that I from a number to a string. And that's just going to print out a little status message. So that's kind of our texty progress bar to indicate like how far we're going, because I get impatient when these things run and I can't tell how long they're going to take. All right, so the real part of this though is going to be, let's create some data that's normally distributed random data that is max n by 1. So in other words, we're going to create 30 participants of random data. Let's say, again, this is just something where we want to t-test against 0 or whatever. And basically what I want to do is now say I'm going to have another for loop from min n to max n. So for everybody between participants 5 and 30, what I'm going to do is take the first 5, the first 6, the first 7, the first 8, the first 9, the first 10, etc. participants in that sample, and do a t-test to see if the first, the first 1 through j participants show a significant effect. All right, and I'm just going to store that for now, and then what we're going to do is peek at the data and play with it and see what we find. Okay, so let's say, now this is a little bit of a tricky line of, well, let's split it up a little bit. So let's say H and P equals, and they like it to separate by commas, so we'll do that, equals t-test of, let's actually split it up a bit more. Let's say this data equals, so basically we want to take the first 1 through j elements in our data, right? So whatever j is, could be 5, 6, 7, 8, 9, 10. We're going to take the first 5, 6, 7, 8, 9, 10, etc. subjects. That's the data we're going to test. So we're going to t-test this data against 0. That's fine. And then we're going to say, let's store this in our matrix. So let's say H is I comma j. That's iterations by number of participants, basically. So H is I comma j equals H. P is I comma j equals P. All right. And then I'm going to do another little trick that you guys haven't seen before, I don't think. There's a command called keyboard. And what keyboard basically does is it just automatically pops you into the Matlab debugger. So if you've calculated some data inside of a function and you just want to force Matlab to go into the debugger and give you keyboard control, you can do that. Now, the other thing I could do is I could just set a breakpoint down here on some line that does something else. But keyboard basically gives me, stops the code right there and gives me keyboard command of what's going on. So basically what I'm going to do is I'm going to run all this sample data and then I'm going to get keyboard control. So let's see how quickly this runs, and if it's super slow. Yeah, it's a bit slow with the podcasting software. You guys will probably find it goes much faster. So what we're essentially going to want to do is see whether we confirm our our hypothesis more often than we would expect by chance, right? So again, what we're doing is basically, because might have gone kind of quickly through this, so I'll go over this again while we're waiting on the set to generate. Generate a random data set with 30 participants, right? Then J goes between 5 and 30. Then we say, all right, we're going to take a subset of that data called this data, which is the first J participants. So the first 5, the first 6, first 7, and so forth. T-test that data set against 0 and store whether or not we found a result in H and our exact p-value in P. Oh, there we go. All right, and then basically we're saving a matrix of all of our H's and all of our P's, right? So what we get in the end, you see that H's is 2,000 by 30, right? So this is whether or not we confirmed our hypothesis for each of our 2,000 iterations for each sample between 5 and 30 people, although 0 to 30 is the size, or 1 to 30 is the size of the matrix. And then our p-values for all those tests, right? So now let's do a couple things. So the first thing we could do, if in theory, so let's first imagine like any given sample size, whether we decided to just collect 5 people, 10 people, whatever, any given sample size should have an average false positive rate of 0.05, right? So one thing we could do is if we said, all right, for all these sample sizes, if we just average over the 2,000 iterations, so we just take the mean of our H's, whether or not our hypothesis was confirmed, that should come out to about 0.05 for all of our sample sizes. And look, it does, right? So, there's some minor variation, 0.0505, 0.05 exactly, 0.054, 0.045, but that's just, random fluctuation. So each of our sample sizes between 5 and 30 does have a false positive rate of 0.05. But the question is really, so what we have here, and this is actually one thing you can do, if you want to, is you can visualize this as an image. So if we want to try to visualize what these H's look like, we could actually do, oops, that's not a very good way to do it. It does work actually, but it's kind of long and skinny. Let's, because our screen's a little bit wider than it is tall, let's flip it this way. Gets it a little bit better. So one thing you could do is say, all right, well here's our data visualized. That's not actually so easy to see, I guess. Basically, what we have here is from left to right is our 2,000 iterations, and vertically is our hypothesis tests, whether they are, basically what you'll see is a white dot whenever the hypothesis is confirmed, and a black dot whenever it's not, right? And the main question is, if we stop, whenever we see a significant result, if we just increase our sample by 1 participant each time, we would actually claim that we found a significant result on any any column of this rather, that has any white dots at all, right? So we know that for any given sample size, the false positive rate is only 0.05, but if we stop at any point on the row where we get a significant result, even if it's only one person that briefly makes it significant and then everybody else makes it not significant, we're going to get an inflated false positive rate. So what we can do, if we want to know that, is what we're basically asking is if any, so for each row of data, so for our 2,000 iterations, we have 30 tests from, or 25 tests from 5 participants, 6 participants, 7 participants. So we want to really know if any of those H's is true. And we can actually do this with the any command. So any says if any of these H's is 1, then the result is 1. But I think this does it the wrong way. Yeah, so that tells us the wrong thing. So we need to do it in the other dimension of H's, which it's a little bit complicated what this does. But basically what this does is it says, all right, for each row, if we do, what the any command does is, for each row, And the 2 here tells any to do this either by row or by column. So this, if we say any of h's comma 2, it says for each row, anywhere that there's a 1 anywhere on the row, give me a 1, right? So we should have 2,000 listings of 1s and 0s, right? Telling us whether or not there's a, we found a true, or not a true hypothesis, but a confirmation of our hypothesis anywhere on that row. So then if we take the mean of that, that doesn't look right at all. Oh, you know why? Because I used the wrong one. So if we take the mean of that, we get a 23% false positive rate. Okay, so that's the moral of the story basically, is with a quick little simulation, if your policy really is, I'm going to collect 5 participants, then add 1 participant on, and I'm going to go up till 30 and stop as soon as I get a significant result, you actually don't have a 5% false positive rate. You have a 23% false positive rate, right? Which is a problem for you if you are, trying to do real research. So the details of that demo might be a little bit tricky for you, but it's pretty problematic. Now, one thing we could actually do is see how that false positive rate grows as we increase our sample size. So what we'd have to do there is make a little for loop. Let's say false pos equals. Well, let's not worry about exactly how good our efficient our algorithm is, because it doesn't really matter. So let's say for let's say false pos is going to be 30 zeros. Okay, so then for I equals 1 or equals 5 to 30. So let's just see what our false positive rate is. The more we do this, right? So for every time that we say, well, let's just collect 1 more participant, let's see how that inflates our false positive rate. So let's say false pos I equals, let's see, that's going to be the mean of any of h's. Now this is again getting a little complicated for you guys, I know, but just hold with me here. So all rows of h's, but the 1 through I columns. Do that across the second dimension of any. All right, that should be right. All right, so now if we use our old friend the plot command, what we find is, now we have a 0 false positive rate for 1 through 4, because we said we were only going to start with the first 5 participants. What we find though is that there's a pretty steady increase. It kind of levels off. I don't know if there's a mathematical equation that governs this, but if you collect 5 participants and t-test them and stop, you do have a 5% false positive rate. But then if you say, I'm going to take 1 more participant, then you've got maybe like a 6 or 7% false positive rate. If you keep doing that until you have 10 participants, you're up to like a 13% false positive rate, right? At 15 participants, you're up to like, what is that, a 17 or 18% false positive rate. At 20, you're up to a 20% false positive rate. 25, it kind of levels off a little bit. You're at like a 21% false positive rate. And at 30, you're up to like that 23% or so false positive rate. So, the longer you do this, the more likely it is you'll get a false positive. Now, it'll probably level off at like 30% or 35% or something, but still a little problematic, right, for our, if we actually do this in real life. Okay, now for your problem set, I realize I've neglected to get into a couple of things that I wanted to show you for the problem set, but one thing that you're going to have to use for the problem set is just this basic plot command, right? So you don't have to do anything very complicated for the problem set. What you're plotting is sound data, right? And we've actually done that before. What I can do is actually go in and let's go into lecture 17 code and just load in some sound data, because I do want to make sure everyone's on board with this. So wave read, let's see, it's just, yeah. Let's just read in like da.wave, because we've got to wrap up here pretty soon, but let's just make sure. All right, so just to make sure you've got enough to do your problem set. So we've done the plot thing before with sound data, right? So that's not very hard to do. And actually, there's a couple tricks you can do. I mean, there's a million things you can do with the plot command. If you're interested, you can see, we do help plot, and see there's a million different options. So if I wanted to plot, let's go back to what I was plotting before, which was the false positive rates. If I want to plot the false positive rates in red, I can tell it, like by default it plots in blue, but if I want to tell it like R, I can do it in red. If I tell it G, I can do it in green. There are a bunch of different color codes you can use. If I want to plot a second thing on top of that, I can use this hold command. Hold on, what that says is, basically, when I draw into this figure again, don't take off what was already there, add to it. So if I want to plot like, what do I want to plot? Like just a linear range from like, let's just plot from like 0.01 to 0.30 or something like that, just as an illustration. So let's plot the numbers 0.01 to 0.30 in blue with the hold on. Whoops, where did it go? Should have done it. Oh, 0.01 by 0.01s. Sorry. All right, so that'll add another plot to the same plot. So if you wanted to do something like, what did we read in before? We read in da. So if we want to read in ga.wave and first plot where is it? Plot. So plot da in blue, and then turn the hold. Oh wait. So I have to turn the hold off from that other stuff, or do this. CLF clears the figure, or you can just close the figure. Any of those. So let's plot da. Right, just like that. And then we want to turn the hold on and plot ga on the same axes. Oops, well, see, I meant to do it in a different color. All right, hold on. Not you guys holding on, the command hold on. So plot the second sound wave in red. So you see now you can see kind of where the two sound waves overlap. Now, of course, you guys are told to plot certain subsets of the data. So you're going to have to figure out how to get just a certain number of elements of that data to plot, right? But it shouldn't be too terribly difficult for you to do that, because in theory you should know how to get the first element of an item, the first 10 elements of an item, the first 50 elements of a Matlab matrix. You should kind of know how to do that by now. So hopefully you can do that once you know how to use the plot command. Okay, well, we didn't get to the rest of our Monte Carlo. I had some really exciting Monte Carlo demos, but I think I'll spare you guys this time because, we don't want to get too crazy. Oh, the last thing I should mention, though, is that if you do want to then save these to turn them in, there's a convenient save command up here where you can save these as, if you save it as a .fig, you can only open up in Matlab, but if you can, you can save it as all these other things. So PNG is a pretty good file format. Let's just call this sound waves overlaid. Let's see how that looks. And let's see if that looks good enough to turn in. Because Matlab's got a million different settings for how it prints these figures out to a... All right, not bad. Good enough for my purposes. So you can just do that. But basically, if you just go up here, you can save in different other formats. You can... Oh, wait. Well, you can't print, but you can... here you can go to your export setup if you want to and change your settings in theory. So you can say, like, somewhere in here you can set your pixels per inch and so forth, although I'm, of course, resolution. So you can set it to 600 dpi or whatever resolution you want right there. But that should give you everything I think you need to know to, or you can just use print screen, but Matlab will let you just save it directly, so may as well just use the save command. Okay, so the last thing I just wanted to note is that you can use, so let's just put out the debugger here. So, we didn't really have time to get into the details, but I did just want to show you that you can use Matlab to do some kind of cool things. I mean, they're not that cool, I suppose, but you can do things like these bar graphs are all generated by Matlab. I won't go through the script that actually does it, but it's pretty nice. Well, actually, it only takes like 2 seconds. We can do it. It's pretty nice when you've got something like this done that you can just say, all right, because I had to make these bar graphs for all these different brain areas that we had data for. So, if I want to, actually, let's get the same area in that graph. Let's just plot these values. So I'm going to go into Matlab and say my data equals that data that I just pasted in from Excel. And I'm going to go into where the script is. Oh, shoot. Oh, sorry, it's on the desktop, isn't it? CD. Desktop. So I made a script I called Figurizer, and I'm going to give it my data, and I'm going to tell it I want bars that are red, green, blue, yellow, and 50% gray. In real life, I had like stripy bars, but that gets a little bit more complicated. So I just hit that command. Takes a second, gives me a little beep at the end when it's done. Beep. So that lets me know my file is created. And then I've got some pretty nice, not the best looking bar graphs in the world, but perfectly nice bar graphs right there that we made in like 5 seconds, right? Rather than having to click a bunch of buttons in Excel. So it's kind of nice when you know how to do that stuff. And you can make all kinds of things. So like, you can line. Oh, we didn't really get to. Well, we did. So you can use. This is basically when you use the plot command and turn on a bunch of the options. You can make plots like this, right? Which look a lot more professional than the kind of dinky plots that you get by default. You can change your resolution, change your font, change the background. You can overlay multiple things. So this is like ERP plots where the bold parts of the lines are significantly different and the non-bold parts are not. So you can use it for ERP plots. This is the actual graph I generated. I wrote another script to replace the colors, replace certain solid colors with stripes. So you can do things like that if you want to get fancy. You can get really fancy and do things like this that is just showing like the significance of various brain waves at various time points in a visual fashion. So basically, everywhere that's blue in this graph is a significant difference between conditions. You can do all kinds of nutty stuff like that if you really want to get into the deep, dark underbelly of Matlab for doing all this stuff. So anyway, so that's not much on data analysis and such for such a glorious piece of software, but it's enough to get you through the problem set and probably more than what you want. So I think we are probably good for the day. So any other final questions? Anything like that? All right, well, podcast viewers, that's it for me. I bid you adieu, so hope you've enjoyed. You guys, I'll see you all next week, so we won't say farewell just yet. All right, so happy programming, and adios.